Hey guys, so this week we are going to be starting latent growth curve modeling. We're going to keep it fairly simple for this first one. Let's talk a little bit about what latent growth curve modeling is. So latent growth curve modeling grew out of the need to model growth trajectories amongst children, actually. So it comes from the developmental research area. Um, the whole purpose is to look at change across time or model change across time. I know when we think of latent growth curves and when you think of the growth curves that you see at the doctor's office or something, which incidentally, those are based off of this type of modeling, we tend to think of these kind of interesting curvilinear effects, and we are going to talk about how to calculate or examine test curvilinear effects. But for the most part, a latent growth curve model is really a linear trend across time. There are specific slopes that you can add that will look at kind of transitions in those trends, or quadratic effects or curvilinear effects in those trends. But for the most part, what we're going to be talking about is straight linear effects. So at its core, latent growth curve modeling is just an extension of a basic repeated measures ANOVA. And in fact, if you see some of these, especially if you see them kind of graphed out, they look an awful lot like a repeated measures ANOVA. It tells you basically the exact same thing. If you were to constrain all the random effects to be non-random, then it would actually map onto a repeated measures ANOVA exactly. Without that, it does map onto a repeated measures ANOVA with random effects, or at least with a random intercept. However, there's a lot of advantages to looking at latent growth curves over repeated measures ANOVA. So some of these are latent growth curves allow you to be more flexible with the intercepts. And we're going to talk about this in class. We're going to kind of bounce around and look at different intercepts and ways that we can really quickly understand what the mean level is at each kind of time point. ANOVA can't do that. ANOVA doesn't allow you to use slopes and intercepts as your outcome, or to use slopes and intercepts as predictors in other types of models, which you can do with latent growth curve modeling, and which you will do sort of with your homework. The homework this week, we're actually not going to go over that type of model in class. I want to stretch your guys' legs, so to speak, and see if you can come up with this on your own. ANOVAs also can't model simultaneous growth of two different processes. That's actually what your homework is going to be doing, is looking at simultaneous growth. It's called a dual process growth model. And then ANOVAs can't look at interruptions in growth, which we are going to do, they can look at interruptions in growth, but they're just not as flexible in doing so. And we're going to do this today as one of the examples. We're going to look at a piecewise latent growth curve model and look at kind of transitions as a function of that. So let's talk about the basic model. In latent growth curve modeling, we have an intercept, and just like in a regression, we're going to have an intercept and a slope or a series of slopes. And so in latent growth curve modeling, our intercept is actually specified by setting every time point value as 1, and then the intercept will be whatever time point is set as 0 for your slope. Remember that when you do like categorical interactions, or when you have a dummy coded variable in there, whatever is set as 0 winds up being your mean effect, and that's true in latent growth curve modeling as well. This is going to set the true intercept at 0, or whatever 0 value the slope is. I hope that is clear as mud right now. It will become more clear when we're doing this in class. The slope is a little bit different, and I think that some people sometimes get tied up around this idea that these slopes are numbered 0, 1, 2, 3, and so on and so forth. But what we're doing is we're constraining the factor loadings to be some sort of organized equidistance time point that is representative of the time point that you have. And so you might have measurements that occur every month, in which case you could have 12 slopes. I mean 12 time points. You might have one that occurs every year, in which case if you had 12 years, then you would have 12 time points. The idea is that they're spaced equally apart. So if, for example, you measured somebody in January of one year and then didn't measure them again until March of the next year, and then you measured them again in June of the following year, you wouldn't want to space those as 0, 1, 2. You would want to space those using maybe the months or some sort of scale that's consistent with the amount of time that's really elapsed. Um, anyway, what you're doing when you're specifying these numbers is setting the slope as a change from one point to another. It can be extremely flexible when it comes to time. You can also go back and you can recenter time. Let's say, for example, that you have a pre-intervention assessment, then you conduct an intervention, and then you follow somebody for a couple of weeks after the intervention. So you might have a minus 1 at the week before the intervention, a 0 right at the week of intervention, and then a 1 at 1 week and 2 at 2 weeks. So what you actually are talking about right here, the intercept, winds up being the value immediately after or at that intervention rather than having it be over here. And when you do this, you can model kind of changes in the trajectory based on where the person was at when they got the intervention. These are some kind of basic examples. We've all seen this sort of diagram before, right? Where you have your y variable at time point 0, 1, 2, 3, and so on. You have your random intercept and random slope. And then we have all of these individual curves. And so what we're really doing is we are plotting a slope across time for every single person. So they all get an individual slope. And then we are using that to say, like, okay, we have a fixed slope, a slope that everyone has, and we'll also get a variance component of this. And if you have no variance in this random slope, then that means that everybody's slope is basically the same, right? Similarly, if you have no variance in the random intercept, that means everybody's mean level is basically the same. In these diagrams, you can see neither of those things are true. We have a lot of variability in intercept in mean levels, and we also have a lot of variability in slopes, some going up, some coming down, similarly over here. So, all right, we can also look at quadratic effects. And so in a quadratic effect, we're talking about like changes across time or nonlinear growth. These are like the charts that you wind up seeing at your doctor's office, right? And so when we're modeling quadratic effects, we set our intercepts all to 1, like I had said earlier. Then we might have 0, 1, 2, 3, 4. And in the same way that we would actually make a quadratic effect in regression, we're just squaring each one of these. So we have 0, 1, 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, and that allows us to look at changes or quadratic effects across time. We will do one of these in class, so you guys will be able to see a quadratic effect. All right. We also have what are called piecewise latent growth curve models. So in clinical trials, we often observe some sort of disturbance in time. We do this with eating disorder research, actually. So we're looking at emotion leading up to a loss of control eating episode, and then emotion immediately after a loss of control eating episode. And so we have this kind of disjointed thing where we might see a slope that's negative affect is trending up like this, and then a binge or a loss of control episode happens, and then negative affect starts trending back down. And so we have clearly, if you have a slope that looks like a chevron, you need to account for that in some way. And it's not a curvilinear slope, it's a very clear triangle-shaped type of slope. And so we're going to talk about how we do this in class this week. So we can also model like acceleration and deceleration trajectories by using these piecewise slopes in conjunction with quadratic slopes. And so here's a kind of a simple example of how we might model a piecewise growth. You can see like here we have like very kind of shallow growth, and then at some point after time 7, growth kind of accelerates, and so we have these two different types of slopes. And so we model that using like our linear effect of 0, 1, 2, and at 2 right here we assume that this is where some sort of interrupt occurs, and we're going to hold the rest of these slopes constant at 2, and we're going to go 0, 0, 0, 1, because note we're starting, remember this was 2, this is where the new one starts, right at 0, 0, 1, 2, 3. And so we will do this in class as well. We will model a piecewise growth and have a look at changes as a function of some sort of event that occurs. All right, that is it, guys. I will see you all later this week.